Yeah, thanks for having me. So, first of all, like a disclaimer, I'm a data scientist by trade, and I've been working at the intersection of data science and cybersecurity, and specifically network security, for a few years. But I'm sure you'll know much more than me about some of the things I'm going to discuss. So feel free to chime in or correct me if needed. Hopefully you can see this plot, because I think I tried to make the talk very visual. And what I'm trying to display here is basically sequences of connections or network activities over time, and just to get a visual understanding of whether things are beaconing or not. So this would be like a timeline of how a beacon looks like over time, and this will be the distribution of the intervals between activities. So if we roughly see that they're mostly concentrated in specific duration, it's probably a good indicator of beaconing. And also, perhaps before I move forward, I wanted to do like a quick poll to see how many are familiar with these two things, with Zeek, formerly Bro, the network security monitoring tool. Yeah, good. Okay, so basically it's a big project, but basically it's a tool that allows you to monitor a network, and it extracts like a series of logs that are useful for threat detection or incident response. And then it's also configurable, so it has like the possibility to write your own scripts and everything. But I'm going to focus mostly on the logs that it generates and how we can leverage those. And then Keras and TensorFlow and machine learning in general, has anyone played with that to build some detections or whatnot? Okay, cool. So first of all, the motivation, then I'm going to go into how we have built a data set to train models that can identify beacons, and how the model is actually trained, and then some of the findings in my own home lab, which is basically my own home connection. So you get to be a little bit nosy and see what's going on at home. And then also some pickups that I found out there. So for me, at least, it started trying to identify C2 frameworks, where you tend to have a C2 server and then some compromised machine or victim machines that is beaconing out to the C2 server and basically requesting commands, right? Saying, do you have any command for me? If you have it, send it, and then I'll execute it and then give you back the result. And I have played with a number of these to try to see what the network activity looks like, or the traces look like Caldera, Meterpreter within the Metasploit frameworks, Lever, Empire, Cobalt Strike, and the reality is that there's actually many of these. So this is a very good resource, the C2 Matrix, and it basically lists like 130 plus frameworks or so. And then you have a lot of tutorials out there on how to set those up to be able to create your own C2s. And this is a snapshot of what Caldera in particular looks like. And what is interesting to me, at least from a data perspective, is that you generally have, when you run one of these frameworks, a beaconing period where you have the victim machine that is beaconing out and saying, do you have commands? Do you have commands? Do you have commands? Every now and then, right? And that tends to be periodic. And then if there are commands, then you see these spikes where there are interactions. And there's more back and forth, more connections, more data being sent and received. And the different frameworks have different ways to configure this, where, for example, on the left, I don't know if you can see it, but basically that's Caldera, has a nice UI. You can enter the beaconing frequency, and you can additionally enter a jitter parameter that will make it more random. And they call that a stealthy parameter or stealth parameter. Empire has the same thing. I'm not sure if you can see, but you have different listeners that you can set up over different channels like HTTP, DNS, and many others. And one of the commands you have is the default delay. One of the commands is the delay and the jitter. I think by default is 5 seconds without jitter, but you're free to go and change it. And Meterpreter has the same. I think the default for that is 10 seconds. This is yet another example with Sliver, where here I was playing with generating a beacon for a Linux machine that would reach out to that IP every 30 seconds with a jitter of 5. And what that means, if you look at these timestamps, is that the requests are going to be roughly every 30 seconds, but they could be up to 20 or up to 35 and 5 and down to 20. Sorry, up to 35 and down to 25. So there's going to be some variance that is going to make the detection a little bit more difficult. So if we summarize these observations, we know that we have a lot of frameworks, so building very specific signatures is going to be a challenge. They all at some point need to have those keep alive beacons. And the periodicity changes a lot. Mostly it's configurable, and the defaults also vary. So it's going to go from days to seconds, right? And optionally you're going to have jitter. Then on top of that, you have different channels because you have to monitor like HTTP traffic, but also DNS, SSH, and many others. And you're going to have these mixtures of the beaconing periods where it's just going to be reaching out for commands, and the interactions when the C2, the attacker at the other side might send some commands or scripts. And then you have the additional issue that even if the beacon was perfect, you might have like some latencies or network measurements that were actually going to like modify a little bit of the timestamps. So for me, the idea was, can we build like some generic detection that will work across all of them, right? And for that, we're going to be focusing only on the timestamps, because if we were to bytes information and so on, we would not be able to do that easily across all channels. And the realization for me was that, okay, I know how this beaconing logic works. I can actually recreate it myself and just generate like 1 million or 10 million examples, like covering like a wide range of frequencies, of jittering, of jitter and latencies, so that then I can train a model that will actually have learned from a lot of variations of those patterns. So with that, we can go into the dataset generation. And the idea for training a machine learning model is that you need to provide it with examples of what beaconing looks like, with as much variety as you can, and also examples of what normal connections as in non-beaconing look like as well, right? So I created like a quick heuristic to generate those examples. So the first thing is it's going to sample whether we're going to create a beaconing example or a non-beaconing example. If we sample that it's going to be a beaconing example, it's going to sample again whether it's going to have jitter or not. And I'm going to generate like a series of sequences with beaconing with jitter and beaconing without jitter. And then for the negative class, for the negative examples, it's going to be mostly random sequences. And I had to set some boundaries here, so I decided to initially at least look at only 24 hours worth of data. And within those 24 hours, like the first event would also be sampled like anywhere between the beginning of the day and the end of the day, or beginning of the 24 hours and end of the 24 hours. For the frequency range of the period, I took 10 seconds all the way to 4 hours just to get a starting point. So my idea was to cover or detect beacons that have a periodicity from 10 to 4 hours, 10 seconds to 4 hours. And then for the jittering, again, some parameters, like you want to make it noisy, but perhaps not too noisy so that it's very, very difficult to identify the beacon. And for the network latency, I just applied some random noise where the beacon could happen like anywhere between -2 seconds to +2 seconds in time. And just to get an intuition of what the examples would look like that were synthetically generated, like these are like what we could call perfect beacons, except for the network latency, where you would see like something, for example, with a beaconing, something that beacons every 16 seconds. Of course, if I plot this in like over 24 hours, it just looks like a straight line. But if you look at the distribution of the intervals, it's centered at 16, and you see like a few seconds back and forth where the intervals lie. And then if you pick a longer sequence, this would be, I guess, like 40 minutes or so. And that's what it would look like over time. So here you can really see a pattern. And then same for like close to 4 hours, I guess. This is what it would look like. And these should be the easy ones to detect. These are the ones that would have like some noise. So this is with beaconing but with jitter. So again, like another beacon with a short frequency but with more jitter, it means that this distribution is going to be a little bit more spread. So there's going to be more variance in the intervals between activities. And then if you go to longer beacons or longer frequencies, you see how some of these dots are more separated than others. And that's just because there is some randomness in when the activity happens. And same here. This is with jitter again, but with a very small jitter. So it's going to look almost like a perfect beacon as well. So it covers a wide range. And I did this repeatedly. So I just generated like random sequences or many sequences of jitter up to like 500,000 or so, just to have an enough representative sample. And for the negative examples, it's just mostly random sequences that could have like activities spread over 24 hours in random ways. And of course, the more you generate, the more variance you have, the better for the model. But it could be anything like activities concentrated just at the end of the day, or at the beginning, or scattered throughout. And one more trick that I did is, instead of actually looking at these as an example for the machine learning model, like the 24 hours, I actually looked at the intervals, just because it gives you some robustness to where it starts in the day. So you're going to actually be focusing on the distances or time intervals between activities rather than when they start in the day. And another trick also for the specifics of the machine learning model that were used, I actually scaled that down from seconds to a lower value, or to lower values. That's going to help like the machine learning model itself. Okay, so now we have a data set with positive examples and negative examples, and it's where the magic happens with the CNNs, with the convolutional neural nets. So the idea that I had is that we can leverage some of these deep learning models that look at patterns, right? And these tend to work very well for images or for time series. The idea is that you have examples in your data of what like beaconing looks like and what non-beaconing looks like, but you don't really know how to quantify that, right? So you're basically going to be feeding examples, and you're going to create a network that says, okay, learn some patterns, right, that can identify like combinations or sequences of 4 to 5 consecutive sequences that look like beaconing. And you're going to be creating, or you're going to be declaring those, and you're going to be letting the network actually learn a few what they call filters or functions that try to match specific patterns. In this case, we're seeing a network that has like 3 functions. It's going to be taking a specific filter and moving it throughout the sequence, like one time and time again. And when the input sequence matches one of those filters, it's going to generate a high output, right? In this case, we have like 3 functions here. So you see that this is moving. As it moves, it's generating like outputs in the next layer. And the detection shows actually 3 functions, because we've seen 3 rows here. But we can run as many patterns as we want. In the particular example I'm going to show next, I think it's like 16 or 32 different functions. And the idea is that the same function, the same filter, is going to be moved throughout the sequence. So we can actually detect like beacons in different areas of the sequence. It doesn't have to be at a specific location. So even if we had a sequence of activities that had beaconing at the beginning but not at the end, because we're moving those filters, we should be able to detect those as well. So this is the model specification. When it comes down to it, it's a fairly simple specification with keras in this case. And the key pieces is that it has like 2 layers of these convolutional filters. The first one is going to have 32 filters, which means that we're going to learn 32 patterns of what beaconing looks like. And then there's going to be like another layer that is going to look at the outputs of those filters. And then we're going to learn like 6 more filters. And then we're going to like add some more layers just to be able to train a classifier. And the classifier in this case is going to provide 2 outputs. One output is going to say whether the activity has beaconing in it, and the other is going to say whether it has jitter or not. So by combining those 2 outputs, we can identify beacons without jitter, beacons with jitter, or non-beaconing. I'm also limiting it in this case to the first 100 activities in a sequence. So if we wanted to score or analyze sequences that have more activity, we would have to move that window to cover all the activities. And on my toy or synthetic data set, like the model seems to be learning well. So this is a confusion metric. It's basically going to it's showing like the hits and the misses of the model for both the beaconing output and the jitter output. So if you see like the numbers, like the vast majority of cases fall in the yellow cells. So basically when it was negative, it said negative most of the times. And then when it was positive, it said positive most of the times in both cases. For the jitter, it gets a little bit more confused, but I think it's still fairly good results. But of course, this is on the toy data set. I think what's interesting is to see what happens when we actually put this in or to work with real data. So for that, I actually use my home lab where I have like a Zeek instance deployed. And this is where I have like basically a sensor that is logging all the network traffic that is or that is going through or before my router. And in particular, for this case, I focused on connection logs, DNS, HTTP, and SSL. By the way, Zeek actually logs mostly like everything in the connection log. You're going to have like all TCP, UDP, and ICMP there, but then there's logs that are specific to different protocols. So HTTP is going to have its own log, SSL is going to have its own log, DNS, and there's a myriad of those. There's like 50 different logs that you can get. So it's very detailed information per protocol as well. What I did in this case is I took like the timestamps of each of those events, and then like I tried to model like source and destination. So basically each sequence is going to be defined by like a source and a destination and 24 hours worth of connections between them. In the case of connection logs, you have like the source and destination IPs. In the case of DNS, you can look at the source IP and the query that was done, because in that case the destination IP might be some DNS server, so not as interesting. And I also broke the analysis based on the response code, or the DNS queries that resolved versus the ones that didn't. And for HTTP, you can also take, for example, the source IP and the host name or the destination IP. That's a choice. And same for SSL. In that case, I took the source IP and the server name of the certificate. And these are some results that I got at home. So I first started looking at DNS traffic and looking at all the requests that actually resolved with the no error response code. And what I had like was an output like plotted in that graph that shows on the y-axis how likely it is to be beaconing, and then on the x-axis how likely it is to be beaconing, and on the y-axis how likely it is to have jitter. So the lower corner is actually saying those are beacons without jitter, and the upper right corner is saying those are beacons with jitter. So if we look at something like what like a beacon without jitter looks like, it's something like this. And then I identified, like, perhaps unsurprisingly, like beacons to ul.ntp.org, so the time sync, which I think was expected, but I also identified like quite a few more things. For example, I had like the time apple.com or time windows.com, again, like syncing time, and that happened like every hour, roughly. And then this one was a fun one for me, like the Honeywell. This is actually like the Honeywell home that actually allows me to control my heating remotely, right? So it is actually like some kind of C2 framework, because I can pull up my app and now change the radiators and so on. So I think I haven't deep dived into it, but it's probably doing the same thing as a C2 framework would do, right? It's actually beaconing out every now and then, and I would expect it to be listening for commands from the app to then change the heating configurations. This is a Wi-Fi extender, and this is like calling to the root DNS server every 30 seconds as well. And then perhaps where it's more interesting to analyze is there's a longer tail many times of these findings with jittering, but you can see how there are some sequences that have some beaconing activities, but it's not perfect over time, right? So in that one, for example, you see that there are gaps where maybe the activity was not beaconing all the time. So if you look at the frequencies, many times you're going to see that they're spread across different periods. But I think it's also important to surface those, right? Because the fact that it didn't beacon like all the time doesn't make it less interesting. And this one too, it's difficult you can see it here, but what's happening is that there's actually several connections close in time, and then some that are more spread. So you can see like the big jumps are these guys here, that I think it's every hour or so, but then you have like a lot of connections that are close to each other. I think it's important to also surface those patterns. Okay, so I did another analysis, and I set a flag myself. So this is DNS requests that actually don't resolve, and this is generally like I have found like a good indicator of issues many times. Just because malware sometimes has like hard-coded domains that are no longer active or not yet active. So if you look for those patterns, you sometimes surface those. You can also surface misconfiguration, so it's also a good hygiene use. And in this particular case, what I did just to make sure that the thing was working is I created like a simple script that would actually look up a domain that doesn't exist every 30 seconds just to see whether it would surface it, and it did. And another of the NTP servers was not responding for some reason, but you could also see that beaconing patterns. So you can do the same analysis over the different protocols. In this case, it was using SSL. And I was looking at the pairs of source IPs to server names. And in this case, what it surfaced is the Google Safe Browsing API. So I don't know if you have used this, but basically you can have a local copy of the Google Safe Browsing database or something like that is going to update every 30 seconds with like malicious domains and IPs so that you can do local lookups. So it did surface it, despite the fact that the updates didn't happen exactly every 30 seconds. So there was like a little bit of variance there, but it was able to surface that. And then I also sometimes listen to the search stream as well. So that also was found. This is actually like the Zeek sensor that I'm using that is sending telemetry out. So it also identified that. And something that was also interesting is that the sequence was also not perfect. So there's areas where there's more activity and then areas where the beacons are more spread. But the model somehow had also learned to identify that. And the other one was Humio, which is like synced where I'm sending some of these logs as well. And finally, I did it like I found like a malware pickup of Zeus, so it might be a little bit dated by now. In a post by Active Countermeasures, so they do a lot of analysis with Zeek as well, and they also talk about beaconing. So I think it's a great resource. And this particular pickup had like a trace of Zeus basically for 24 hours. And they basically used that as an example to demo some of the beaconing detection. So I did the same. And sure enough, it identified some beacons. Without jitter, it identified like connections to weather.microsoft.com. And here see how like the activity happens only like in the last half or last third of the 24 hours. But remember, because we were looking at intervals and not where it starts, it gave us some robustness to that. And then, like I guess the malicious domains that they were trying to identify was that second one, like the Mahamaya One Life Sciences or whatnot, that is still reported on VirusSolve, and that one was beaconing every 30 seconds. So it actually only happened at one point of the 24 hours that was shown here, but I zoomed in there just to see like the sequence, what it looked like. And it was fairly straightforward every 30 seconds. And then it identified all the things like Windows updates and so on. So I have also tried this at higher scale, like in production environments and so on. And my experience is that it's good to identify these C2 frameworks, but the reality is that there's many things that actually beacon out. So I think it's more of a good like a building block to then build like more complex detections. And yeah, so things like connectivity checks, service updates, many actually legitimate beacons that would be like my Honeywell at home and so on. So all of those. And then like a lot of the detections that I had found were looking for these perfect intervals between sequences, and I think the reality is a little bit more messy. So if we only look for those, I think we're going to be missing on many interesting activities. So I think it's important to have some flexibility. And CNNs I have found that are good at that, because you're not really specifying upfront what those patterns are that you need to look for. You're just sending the data with that variation and letting the model identify those patterns for you. And I think the last thing is that I think this approach can be identified can be adapted to surface like other patterns that are not necessarily beacons. Like for example, this was a sliver session where it had entered like a remote. This is a remote shell, and I think it's configured to basically have like exponential delays or incremental delays. So basically, it's going to wait for a few seconds for a command. If it doesn't get a command, it's going to wait for twice as much, and then twice as much, and then wait for a long time. So you see that the connections are spread like further and further until there's a big jump. But that whole pattern repeats again and again, right? So those could also be good indicators of some of these reverse shots. Yep. So that's what I had. Like, if you have questions or experiences detecting this theft, I will be very interested.
Yeah. So, like, what kind of anti-pattern could you create to be less obvious?
Yeah, so I think where the model failed is where there is a lot more variance or the ratio, if you want, from the period to the jitter is very high or very low. So basically, if you have like a lot of jitter, maybe period, like a sequence that jitters every 10 seconds, but where the variance is huge, right? That messes up with the model.
How much jitter did you put into your training set?
So I tried ranging from 10,000 examples all the way to 1 million, but I could generate as many.
But how much jitter did you put in?
1 million in the end.
Up to 1 million % jitter.
Sorry?
Up to 1 million % jitter.
Oh, no. 30%, I think. Exactly. Yeah.
I guess a lot of your beacons that you found also had a lot of peaks at zero. So maybe you want to increase your simulation. Let's say that there's a chance that actually when you have one connection, it produces 2, 4, 5, 8 sort of thing. Because otherwise it's throwing the machine learning off to say, if I see something at zero, I know it's not a thing.
Yeah, that is true actually. So you mean at zero, like zero interval or
if
zero?
You go back like 3 slides, I think it was. Oh no, there we'll use that one. So Windows Update, right?
Yeah.
It is a beacon. It's got a little bit of randomness, but also it created multiple connections at a time.
Yeah.
So you've got a big peak at zero on the left there.
Yeah.
Your simulated beacons will never have the peak at zero, but lots of things will actually send out a handful of packets or a handful of connections. Wait and come back. So if you build that into your simulation of it might not just send one thing, it might send 5 things, 10 things, then probably will pick up things like that.
Yeah, I think so, yeah. Well, I think I have also seen where people packetize some of the connections and they basically group all of those together. So I think that's a good point. Yeah.
Did you do anything, for example, you see the beacon goes out, the connection's made, that tracing the component, it's all very well trained in the beacon, but obviously that's all not that interesting in the sense that it's obviously the connection is created afterwards, because obviously may swap to an URL, an IP address. Have you got any correlation between this transaction to this transaction like that?
So I haven't. It's more difficult to generate like those examples. So I have seen that with my own eyes, but it's very difficult because all those frameworks like generate like slightly different patterns. So what I thought is that if we could focus on the beaconing sequence, maybe that's a very strong signal, like in a more robust signal across all the frameworks. But I think the idea is that not only you need to identify that, but also what happens next. And that's also part of the reason why I wanted to be able to, even in a longer sequence, if at some point of the sequence that I was beaconing, I wanted to be able to find it. 2 questions.
So for UDP connections, how did you decide what was a single connection and what was... that sounds a bit more difficult than GCP.
Yeah, so I think it depends on the protocol. For example, DNS, in Zeek at least you have like 1 log for every request. So I was doing it at the request level.
Individual packets.
Yeah. But if for other protocols, I don't know, we'll have to see the specifics.
So I was kind of wondering, so do you see this kind of running on kind of intelligence in a knot, where they're getting logged in from Zeek from various people, and then you can make manual, maybe automatic responses, like turning up the scanning threshold. What I wanted to ask mainly was, is the scanning frequency, is that something you configure in Zeek? Or is this just from the data set?
Yeah, so these I have done like completely outside Zeek. So I took like the Zeek logs as an input and then like did like a layer of analytics on top of that.
Right, but you could use the trained model against live data.
Yeah. So I think the thing is you would have to somehow maintain like a 24-hour window of the timestamp. So in practice, when I have done that, I have filtered down the logs like with some heuristics, right? To say, okay, for HTTP, I'm only going to focus on host names that contain domains that are not popular, for example, because otherwise the loads becomes like huge. You basically need to maintain all the traffic.
And can Zeek do that kind of?
You can do that. Yeah. So there's demonstrations of people using Zeek together with Zeek Broker to then like send to other tools. So you don't really need to do the machine learning piece in Zeek. You can actually, with Broker, send Zeek like events outside Zeek, then process it elsewhere, and then send it back to Zeek. And in Zeek, you can maintain tables and memory with like some some OR cache of activities and timestamps.
SQL normally run it against the live stream. They come up logs for an hour, but those hours then get counted up or archived on, and it then depends how big your data store is. Or I can save a month or 10 terabytes worth of data. For years, almost sacrifice as opposed to last.
Right, guys, we're going to break for lunch now. We're back at half one.